Hello all of you. So in the last class we have been discussing the Monte Carlo scheme in somewhat more detail. We discussed the detailed balance condition and we defined the criteria that the transition probability must follow for the detailed balance to be valid. So now I will take it further, and the goal is to get a workable Monte Carlo scheme, and in the next week we will see how can we numerically implement that. So again, I want to start with the detailed balance condition. That is the number of states going from m to n, that is given by the probability density of states m multiplied with transition probability m pi mn, that should be equal to the number of states going from n to m, that is rho n multiplied with pi nm. So let's choose a pi mn value and see whether it satisfies this. So clearly, as I was telling you, there are multiple ways in which we can pick this. As long as this condition is valid, we can rest assured that the Monte Carlo will kind of work. Whether it is going to be efficient or not, that will depend on the choice of pi, but this condition should be met. If this is not met, at least the weaker condition that we discussed should be met, and so on. Okay. So let's start with one of the original prescriptions by the scientist named Metropolis. It is called Metropolis algorithm, and it goes like this. So pi mn is assumed to be some alpha mn, where alpha is a matrix, for rho n higher than equal to rho m, and is equal to alpha mn rho n by rho m for rho n less than rho m. Right. So let us first check whether this satisfies the detailed balance or not. So let's say we have two states, 1 and 2, and they have some probability density rho 1 and rho 2, and pi 1 2 is transition probability of going from 1 to 2, pi 2 1 is for the opposite, and we are interested in checking whether this particular choice of the algorithm satisfies the detailed balance or not. By the way, Metropolis made one assumption here, and you will see how this is useful. He assumed that alpha is a symmetric matrix. That says alpha mn is equal to alpha nm. So let's do one case where, for example, rho 1 is less than rho 2. Now in this particular case, what I find is pi 1 2. So n is 2 here and m is 1 here, and clearly rho 2 is higher than rho 1. So what it is meaning physically is this state is more probable and this state is less probable. So therefore I will use the first relation because rho n here is greater than rho m. So this will be equal to alpha 1 2. Pi 2 1 on the other hand, now 1 is my n and 2 is my m will be obtained using the second relation, and that will be alpha 2 1 multiplied with rho 1 by rho 2. Now, since alpha 1 2 is equal to alpha 2 1, we can pretty much replace this quantity by alpha 1 2, and if I use now these two expressions, what I have is alpha 1 2 is equal to pi 1 2 and pi 2 1 is alpha 1 2 rho 1 by rho 2. So, I can replace this alpha 1 2 with pi 1 2 using the first equation, and we therefore obtain pi 2 1 multiplied by rho 2 is equal to pi 1 2 multiplied with rho 1. That is exactly the detailed balance condition for this particular case. Now, you can see, even if the opposite were true, where rho 1 was greater than rho 2, then also you will have the same equation. So, then I will use second equation for the first thing here and the first equation for the second thing here, and nonetheless you will have the same equation. What will happen when they are equal? What will happen when they are equal is, when rho 1 is equal to rho 2, then in that case pi 1 2 is equal to alpha 1 2 and pi 2 1 is also equal to alpha 2 1. So, basically pi 1 2 is equal to pi 2 1, and the densities are already equal. So, therefore, again we can get the detailed balance met, right. So, by choosing alpha to be a symmetric matrix, we are making sure that the detailed balance condition is met, but we can choose still alpha to be anything. There is still some room in which we are we have some choice by which alpha can be chosen. Now, let us see why we are doing that for a minute. Why this particular algorithm? So, what exactly it is doing? So, if I look at my pi mn, m is my previous state and n is my current state, and I am keeping as alpha mn when the probability of the current state is greater than equal to the probability of the previous state. On the other hand, I am multiplying this quantity by rho n by rho m when rho n is less than rho m, right. And now, I am referring to the stationary rho distribution, right. So, of course, I will begin with something else, but ultimately we reach stationary state. So, at stationary state, what do I want to do? So, I want to sample more in the region where you have higher probability densities, and we want to sample less in regions which will have lower probabilities, right. So, if the states have less probability to happen, then why do I want to sample there more, right. So, therefore, when the probability in the current state, that is like I am starting from previous state and I am making some kind of a movement from or transition from that state to the current state. So, if the probability in the current state happens to be less than the previous state, so that means that I am trying to move to a state of a lower probability, I am multiplying with rho n by rho m, and as the ratio of probability of the current versus the previous decreases, I am basically using a smaller transition probability. in the limit when rho n is very smaller than rho m, in that case there will be very less probability of going from m to n. So, over a period of time, what is going to happen is, and by time here I mean the computation time, is what is going to happen is I will be sampling more and more in the regions of higher probability, and when we are at the stationary solution, then also I am sampling in regions of higher probability more than in regions of lower probability. So, essentially this rho n by rho m basically is able to weight my transition probability in a manner that gives more preference to the transitions from a state of low probability to high probability, because I did not add any factor here, and gives less preference to movements from high probability to less probability, right. Keep in mind that the movements or transitions may still happen. So, it is not completely stopping that to happen, right. So, I can go from a state of high probability to low probability, because that happens to be important for the condition of detailed balance, but the transition probability decreases for those kind of movements as opposed to the movements from states of low probability to states of higher probability. That is, I would say, a very important point. Now, let us see how exactly we will do that in practice, right. So, all of this so far is kind of very theoretical. Let us say I want to apply this Metropolis algorithm in practice. How will I start? So, just like molecular dynamics simulation, I can still imagine that there would be a box and there would be particles in the box. The setting up of the system when I begin may look very similar to the molecular dynamics setup, right. So, as soon as I do that, clearly I am at a particular state gamma, let me call it some gamma initial. Now, however, unlike molecular dynamics, I will not solve the Newton's laws of motion. What I say, this system starting from here can go to many possible states. So, let us say I have numbered the states gamma 1, gamma 2, gamma 3 to some gamma m. This gamma initial could be any gamma I, where I is in the range 1 to m, right. So, any one of them could have been picked whenever I am doing the simulation setup, right. How exactly we will do that, we will come back to that point. One of the possibilities is we randomly generate particles in a cube. We will revisit that point, but keep in mind that whatever my initial gamma is, that is chosen among the state space. Now, I will make some movement, and that is artificial movement, nothing to do with the actual dynamics of system, that leads to a transition from this initial state to some new state. So, let us say for example, one of the possibility is I started from some gamma 2, from here I go to gamma 4, and since it is a Markov process, now when I am at gamma 4, I do not care whether I come from gamma 2 or gamma 3, the memory, there is no memory of the previous step. So, now from gamma 4 again I can go to any of the possibilities. Let us say if I go to gamma 3, and from there let us say if I go to gamma 5 and so on, and I will continue this kind of a process, right. One of the possibilities by which this can be done is that I pick one of the particles and I move it in a random direction, right, and we will take particular cases in more detail, but this is one of the schemes, right. So, at any given step I pick one of the particles and move it a bit, right? As soon as I am doing that, I am disturbing the phase point, because phase point was PQ, right? And now I move to a new coordinate. By the way, momentum doesn't play any role in Monte Carlo because there is no dynamics here, so as to speak. So coordinates are the only thing of concern. So once I have moved one point from here to there, I have moved in my state from something to something else. Now clearly that state has to be among one of the state space, right? So whatever movement I am doing should consider how I have constructed my state space. I should be making that happen there. But let's say if it is going to a valid state in my state space, then when I go to the next step, I can again pick some other particle and I can move it randomly in any one of the direction. I can pick how much to move and I can pick the direction as long as I am going to a new state, and as well I can remain wherever I am. So then how it is a Monte Carlo scheme, how we have lost memory. The way we have lost memory is in any given step I am picking a random particle from the box and I am moving it in a random direction. In the next step, I don't care what happened previously, I again pick a new particle randomly and again move in random direction, right? So it doesn't really matter what happened previously whenever I am making the new step. That's what I say, it's a Markov process. Now clearly, if this is what I am doing, then let's say if I repeat the simulation, let's say if I rerun my code, again what will happen is I will pick a new particle randomly and I will move it. Now this time, since it's a random generation, random picking of particle and a random movement, the new movement is not going to be the same as what happened in the previous Monte Carlo simulation, right? So if I repeat this, I may follow some other pathway. Let's say this, right? So every time I am running my Monte Carlo simulation, I am essentially sampling different regions of the phase space, and that is where Monte Carlo is quite different from molecular dynamics. In molecular dynamics, it is fully deterministic because we are solving Newton's laws of motion. As soon as we pick the initial state, we are doing the true dynamics, so we know where we will go. In a Monte Carlo simulation, since we are doing a random generation or random picking and random movement, every time I am doing it, I am essentially capturing different regions in the phase space, right? And since there is no memory of the previous step, I can pretty much go in a very zigzag manner in the phase space as opposed to a more deterministic movement in the case of a molecular dynamics simulation. So let's say if this is the Monte Carlo scheme that I am doing, in that case, let's see what the densities should look like. So let's say I start with this system and I have moved this particle from here to there. So there are two states, a new state where this particular particle has moved, and an old state where this particular particle is here. By the way, the state is a representation of coordinates of all the particles in the system, right? So even though I am labeling this as gamma old and gamma new, this is referring to all the coordinates of all the particles in the system in the new state. Although I am moving only one, everything else has changed in the system because all the forces that involve this particular particle will change, the separations have changed. So it is not that the motion of every particle is somewhat individual. The motion of every particle, even if it is artificial movement as in Monte Carlo, it is affecting the entire system behavior. Now let's say the energy in the old state was some u gamma nu, let me call it some u nu, and energy in the new state, in the old state, is some u old. So now what do we expect when we are in the stationary state? What we expect is the probability in the new state should be proportional to the Boltzmann factor, that is, my rho nu should go like exponential of minus u gamma nu, and my rho old should go like exponential of minus u gamma old. In fact, if I want to find the actual value, I have to know the partition function. But if I am only concerned about the ratio of these densities, then that denominator will cancel, right? So, my rho nu by rho old can therefore be written as exponential of minus u, by the way, there is a kBt here, u gamma nu minus u gamma old divided by kBt. You can represent this quantity as some delta u, that is the energy change from the old state to the new state. This is going to be exponential of minus delta u by kBt. Now, let us go back to the Metropolis algorithm. I have said my transition probability is alpha mn when rho n is greater than equal to rho m, and it is equal to alpha mn multiplied with rho n by rho m when rho n is less than mn. So, what is going to be the transition probability therefore of going from a old state to a new state? So, if the new state happens to have rho n greater than rho m, then in that case we will have the probability as alpha mn. And when will that happen? That will happen when delta u is less than 0, because when delta u is less than 0, then this exponential quantity is going to be larger than 1. That means the rho nu is more than rho old. So, this quantity will be alpha, and now it is a symmetric matrix. So, it is alpha new to old or old to new, whatever you want to write, multiplied with, so that is why I put a double arrow, keeping that alpha is same either way, multiply this quantity when delta u is less than 0, and this is alpha new to old. And when this will happen? When rho n is less than rho m, when rho nu by rho old is less than 1. And when will that happen? That will happen when delta u is higher than 0, right? By the way, we can say delta u less than equal to 0 here, because we had a greater than equal to here. So, this multiplied with exponential of minus delta u divided by kBt when delta u greater than 0. So, now how will I therefore implement that? What is that alpha that is there? Now, alpha in a sense that we have already chosen. So, when I was making the movement, I was making with some mechanism, I was picking a random direction. On a computer, there can be only certain number of direction. I mean, it's going to be continuous, but on computer it has to be discrete, right? So let's say there are 1 million possible ways in which I can move a particle in any of those directions, right? So every time I am making a random move, the probability of that to happen is 1 by that million, right? So alpha is determined by how I am doing the Monte Carlo movement. Everything else is well determined because I can find the energy changes once I know the coordinates, and coordinates are known because I start with an initial coordinates and I know how I am making a movement. So the coordinates are known, alpha is ensured. The only thing we have to make sure in choosing alpha is the reverse should be possible. That's when it is symmetric. So let's say, for example, if there is some probability of a particle going to the right, the probability of it going to the left should be equal, as long as there is no directionality or some bias in the way I am choosing to move a particle. There is no problem. Now the transition has to be happening with the probability that we have listed. Now how will we make sure, let's say if pi is 0.01, how will we make sure that I will make that transition with a probability of 0.01, right? So the answer to this lies in here. So let's say, for example, if pi old to new comes out to be 0.01, right? So alpha refers to the movement, and I am saying that that has to be symmetric. So I should be able to move for every particle to the right or left, top or bottom. There should not be any directionality to this, right? So then how will I ensure the transition probability is 0.01? That means I should be accepting only 1 out of 100 moves that I make. And the answer lies in the word I already used. I only accept those number of moves which are like 1 by 100 in number. So let's say, for example, if I am making 100 movements, I call them a trial movement, and a trial is accepted with a probability of pi. So what I do then is I do not move the particle, I try to move the particle. I just imagine that the particle has moved from here to there. Now what I compute the energy change that would result if that movement is made. Now on the basis of the energy change, we compute pi. That tells me the probability by which this movement should be made. Now with that probability, I accept the move. If the probability is high, I accept more. If the probability is less, I accept less, right? So that acceptance and rejection is something that is novel to Monte Carlo, that doesn't happen in molecular dynamics. In molecular dynamics, when particles move, they move. I mean, there is nothing like I want to move there and then I can judge whether I should go there or not. In a Monte Carlo simulation, we always make a trial movement. I see whether I want to get there or not, and I make the jump from here to there only with a certain probability, right? And this is what makes the Monte Carlo simulation special, because now, as I have been telling you, we have a control on this pi mn in terms of what I was saying. I can have a lower probability of going from a high probable state to a low probability state. So I have that in full control. So I can accept the movements from highly probable regions in phase space to less probable region in phase space with a lower transition probability. On the other hand, the movements from a lower probable region in phase space to higher probable region will be accepted with a higher probability or transition probability, and it is therefore this we will be able to sample the phase space more efficiently. So, before I conclude, there is one detail that is extremely important in both Monte Carlo and molecular dynamics, and that is whenever I say my system is like this, that it contains some molecules, I tend to draw some kind of a box. Imagine that you have some carton containing balls, just make it, scale it down to very small length scales, and the balls you make it like molecules, and they will resemble the system that I am talking about. Now, clearly in molecular dynamics, the molecules are indeed moving. In Monte Carlo, molecules are still given, or particles are still given an artificial movement, and therefore it is quite likely that they will hit the walls of whatever container I am imagining, right? Now, what exactly that means? Does it mean that we really have a cubic container containing the molecules? Probably not, because yes, in principle you can have a cubic container containing the molecules which you are simulating, and in that case that picture is very valid, that the molecules hit the ball and get rebound. But in more general situation, since I have been telling that the number of particles or molecules you can simulate is pretty small, at least not comparable to any macroscopic system you are imagining, in most cases you are doing a tiny bit of a large system. Let us say, for example, if I think of a beaker containing a liquid, I am simulating a small, very tiny volume within that beaker, right? What that means is that there is no walls really, because you can have molecules coming in here, molecules leaving out from there, and so on. In fact, even though the picture suggests that there is a wall, there is in principle no wall. First of all, because there is no physical wall out there, because I am considering a small cross section of the system, and secondly because that system not in isolation. So, that system exchanges molecules with the other nearby systems. Even though I am choosing to simulate one small part of my large volume of any liquid or a solid or whatever, that is not isolated in terms of the exchange of the number of molecules or the energy, right? Even when we discuss the ensemble and all that, all we say that we have certain control variables. That control can be applied for a macroscopic volume. But when we look at that particular cubic box or whatever, we are not trying to suggest that this box exists in isolation. Clearly, that box is, I would say, a small representation of a large macroscopic system. So, it turns out that a better boundary condition is what is known as periodic boundary condition, is a much better bet in these kind of situation. And what this says is that the number of molecules overall in the box remains constant. Yes, molecules can come in, molecules may go out, but overall we can assume that n is constant. So, as long as we have started with a system containing large enough number of molecules, the fluctuation in n is anyway going to be small. So, therefore, keeping n as constant is not really taking away any much realism from the picture that you have. Of course, in the grand canonical ensemble, we will not have n constant and we will make the same assumption there. But for the canonical ensemble, we are keeping n constant, and so we will do in a simulation. But what we say is that, let us say if some molecule want to go out, then some other molecule has to come in to fill the void that is created by that molecule. So let's say this is my box and some molecule is crossing one of the walls, because walls, technically there is no wall, physically there is no wall. So if one molecule leave, something else comes from the opposite end, the other wall, opposite wall, and enters the system. So every molecule that is lost or every particle that is lost is compensated by another particle that comes from the opposite end of the system. And that is the essence of the periodic boundary condition. So what this picture essentially mean, if you want to think about it, is something like this. That is saying that in fact, if I look at the entire system, let's say a beaker or whatever I am trying to simulate, I am simulating only a small part of that system, that is my simulation box, right? That can be a cubic volume, right? And I am now doing in just 2D for the sake of illustration, and this contains some configuration of molecule. So what the periodic boundary condition actually employs is the assumption that the system will be containing many replica of the box that I am simulating, and that fills the entire volume. So I can imagine that the same configuration of the molecule is repeated throughout the volume of the beaker, because whatever I am simulating is a representation of molecules in the beaker. So I may imagine that whatever cubic simulation box I am doing, that is like being repeated throughout the beaker or whatever system I am trying to say. That means every system in there has the same configuration of molecules, so as to speak, right? It has pretty much the same configuration, just being repeated. And all these guys which I am essentially not simulating, so these are basically referred as images of the simulation box. So this is purely a hypothetical picture. For the purpose of simulation, I am only simulating the simulation box in the center, but one can imagine that that same configuration is being repeated throughout the entire volume, and that would be a representation of the bulk system that I am trying to simulate. And it is then we can say that, let's say for example, if one of the particle leaves out, then since the configuration of the images is same as the simulation box, what means is that all these images also undergo the same movement. And since the images also undergo the same movement, as soon as this guy leaves, another guy comes in and fills the void from the other end. That is just an implication of the assumption of the images of the system, right? Now, if you think about it, this is not really, that is something that is highly realistic, because in some sense what I am assuming is some sort of a crystalline behavior, because I am saying that the configurations are being repeated. The only difference from real crystals is that crystallinity is applied over units of the simulation box that contains huge number of molecules, right? So a crystal will have repeating units of the order of 1 or 2 molecules, but in this case I am assuming that there are millions or billions of particles in simulation box that characterize its configuration, and that entire thing is being repeated, right? So yes, it is introducing some kind of crystalline behavior, but it is much better than assuming that there is a physical wall where particles hit and get rebounded, because there is no wall in reality. So that is one of the points here. The second point that also comes from the periodic boundary condition is this sets a limitation on the shape of the box, because ultimately I am trying to represent the actual system, that is the beaker I was giving the example of, by using the simulation box and replicas of that or images of that. So, I am basically trying to fill the beaker with repetition of the simulation box. That will be valid if the shape of the simulation box is such that it is space filling. That means I can stock, like hypothetically speaking, I can stack many cubes or cubical cartons and I can fill the entire space. If that is possible, then we say that shape of simulation box is space filling. So, cube naturally is therefore space filling. On the other hand, let us say if I would have taken my simulation box to be spherical. In that case, you may imagine that let us say if this is my simulation box, now this thing will repeat. So, you will have images on all sides, but you will also have regions of like some kind of a void that has no physical meaning. What if a molecule happens to go here? What will we do with those molecules? It is neither the simulation box nor its image. So, the periodic boundary condition will not work in that situation. So, therefore, the assumption of the periodic boundary condition requires that my simulation box is space filling, and cubic is clearly a great choice, but it does not have to be cube. It can be many other kinds of shape, but clearly not a spherical shape, because the spherical shape will not fill the entire volume. Okay. So, periodic boundary condition is employed, I would say, in most of the simulations. However, if I want to simulate things like interfaces, where clearly the behavior is not of a repetition, there is a discontinuity in the behavior as soon as an interface comes in. So, in those situations, the idea of the periodic boundary condition will not work. It may still work in the other directions apart from the interface direction, but it will not work in along the interface, across the interface. That is one of the limitations. And secondly, in many cases, the use of periodic boundary condition is not even needed, because I am more interested in the behavior around a molecule. Let us say, for example, I am simulating a protein and I am interested in how the protein interacts with the solvent around it. So, I am not interested in something like protein in bulk and I am trying to simulate one small representation of that thing. Instead, my interest is in knowing how protein interacts with the solvent molecules. In those cases, I do not need to make this sort of a representation, because there is no macroscopic system I am trying to simulate. I want to get a behavior that can be gotten with much simpler boundary conditions, and actually in that case more realistic boundary condition. And it turns out that in that case we also do not need a space filling box. You can just take a protein molecule and some solvent molecules around it to solvate the protein molecule and so on. That also works pretty well. And in special situations, we also know some other types of boundary conditions. For example, a reflexive boundary condition, that is pretty much a rebound kind of a arrangement. We can also add the effect of actual physical walls if they are present by applying spatial wall boundary conditions and so on. We will discuss them briefly later in the course. So, with that, I want to conclude the discussion today. And in the next lecture, we will see how do we actually numerically implement a Monte Carlo simulation, and after that we will be doing some case studies around this idea. So, I want to conclude with this. Thank you.